Hello everybody. So today we're going to be looking at features of graphs, and things that we'll be looking at are limits, continuity and differentiability. I find with this topic, once it clicks in your brain, it's pretty easy, but it does for some people take a little bit to click into their brain, especially the limits. It takes a little bit for you to see exactly what's going on, and once you see it, it's not very hard at all. So we'll be using a graph to kind of help us understand what these terms mean, because they can seem a little bit confusing just reading them. So they are to do with the graphs of functions. So if we just look at this graph here, f of x, it might seem weird, like it's going up here, it's got a hole and a dot, it's got a line coming down like this. So it's hard to give an example of kind of where you might see one of these graphs. Kind of like a distance time graph sometimes can look pretty weird like this. It wouldn't have an asymptote, but they do exist, and we need to be able to kind of still find gradients and different things to do with these graphs. So these three things are quite important. A few things: if you see a circular hole like that, and then there's a solid hole below it, it means that at that point, when x equals -4, the graph jumps. So it's going along here, and then at that point it jumps down there, and then straight away afterwards it continues back up there. And there's going to be an asymptote on the y-axis up here. This graph's going to go up for infinity. As soon as it kind of jumps over there, it's down here and goes up. So let's look at continuity first. It's quite an easy one, pretty straightforward. So a function is continuous if its graph can be drawn without lifting pen from paper. It is discontinuous in any holes or jumps. So overall, this graph would be discontinuous, because there's a jump here and a jump from there down to there, or a hole here and a jump. But actually, like the graph, we would say the graph is continuous everywhere except at a few points. So it would not be continuous, or it would be discontinuous when x equals -4 at this jump, and when x equals 0. So the graph would continue going all the way up towards infinity as x gets closer to 0 from there. As soon as it gets there, it jumps down to this point here, so it jumps. So those 2 points would be where it is discontinuous. So we're going to write that down here. We'll do some examples kind of as we go. Make sure I haven't moved that out. Alright, so my answer to this question would be when x equals -4, or when x equals 0. And I'll just do them as 2 points. So for what values of x is f of x discontinuous? -4, 0. Everywhere else you could draw this graph without lifting your pen. I'd have to jump here, I'd have to jump here, but everywhere else I could draw it just by keeping my pen on the paper, so it's continuous everywhere else. So that's what continuity is. Pretty straightforward. Good. Differentiability. So this is to do with, can I find a gradient at all the points on this graph? And there are certain points where we cannot find the gradient. So a function is not differentiable. We cannot find its gradient at any point where it is not continuous. So any of my points that I said it wasn't continuous, it is also not differentiable. It's also not differentiable where the graph has any sharp corners. So if you see anything like this, then it is not differentiable. Even if it kind of looks like this, not differentiable. If you see a corner, proper corner, it is not differentiable. So the reason for that, like if we look here at x equals 3, there's obviously a corner here. So if I tried to find the gradient when x equals 3, the question is it the gradient going this way, or is it the gradient going this way? And so we actually don't know which gradient to take. We don't know if at this point we're looking at this gradient or if we're looking at this gradient. One would be positive going up, one would be negative going down. So at that exact point on that corner, we do not have a gradient. We do not know. It's an ambiguity. so it's not differentiable there. It would also not be differentiable here. Same reason. Is it this gradient or is it this gradient? And then it's not differentiable for pretty much the same reason where it's discontinuous. At x equals 0, we don't know where the graph is, let alone do we know what its gradient, and also at -4. So there would be 4 points on this graph where it is not differentiable. Pretty much these questions go hand in hand. They're usually asked one after each other, so you can always just put the non-continuous ones straight there because they'll always be there. And then it's my other 2 corner pieces, so it would be 3 and 4. Good. Let's do another example of just these before we get to limits, because limits can get a little bit confusing. So let's do another picture. Try and answer these 2 questions. Alright, so continuous, or where is it discontinuous? We're looking for jumps or holes. So it's going along, jumps at 2. So when x equals 2, it has a jump. It goes from here up to here. Also at 3. Jumps back from there down to there. Everywhere else I could draw this graph without lifting my pen. Just at those 2 points I have to jump. So straight away for not differentiable, I'm going to put those exact same 2 points down. And then I have to add in any corners. So the only corner I see is here at 1. Has a corner there, so we're going to add 1 to that list. 3 points where it's not differentiable. Everywhere else, technically, I could find a gradient of that graph. Alright, so now we're going to look at limits. The definition of limits is very confusing, so it's much easier to see me doing it with a graph, but we will talk through the definition of limits. So, the limit of a function f of x as x tends towards a, or goes towards a, is what that arrow means, and a is a point. So the limit of a function f of x as x goes towards a point a is the value that f of x gets very close to as x gets very close to a. So we're not looking at the point a, we're looking very close to that point and seeing where the graph gets close to. We say a limit does not exist if f of x does not head towards the same value from the left as it does from the right. So this is confusing. Let's look at an example. I'm going to fold this just so we can keep the words there. So if we look at this graph, usually we look at limits at weird places, like at holes, at jumps. These are the points where we usually need a limit. A limit is usually to help us find kind of what the graph would be doing if we don't know at that moment what it actually does. So the limit of a function f of x as x goes towards a. So we're going to start with this point -4, because it's a weird point. The graph jumps there. So a limit is trying to find out kind of what the graph is doing really, really close to the point -4, not exactly at -4. So if I was, so the technique is basically you find the graph either side of that. So -4 is here, I'm going to go either side of -4 and just keep my fingers on the graph. So where the graph is. And then I come towards that -4 point. If I stayed on that graph and I followed it towards x equals -4, it seems like the graph is heading towards 1. So the graph is tending towards 1. Although at that point it jumps down here to -1. The limit is concerned with this 1 point. It's not concerned with actually where the graph is. It's looking at where the graph was heading. So the graph was heading towards 1. So we say the limit as x approaches -4 is 1. It's the value that f of x gets very close to as x gets close to -4 in this case. So the graph gets very, very, very close to 1. So that's what we write. So down here, make sure you can see it on the camera. what is the value, what is the limit of f of x as x goes towards -4? This would equal 1. That's how we write it. So they write it like this. What is the limit of f of x as x goes towards -4? 1. Now another case is going to be when x goes to 0. That's another interesting case on this graph. Just trying to get it all on the screen. So, as x goes to 0, this is another point where the graph jumps here. Now the issue is with this one is if I go either side of 0, I'm ending up on this side and I'm ending up here. So if I kind of go back and I follow the graphs towards 0, you'll notice they go to totally different places. From the left it's going up towards infinity, from the right it's coming back down to 0. So in this case here, what do I pick? Do I pick 0 or do I pick infinity? Which one is it? So this is the case where there is no limit. This is the case a limit does not exist if f of x does not head towards the same value from the left as it does from the right. From the left it's going to infinity, from the right it's going to 0. Therefore, there is no limit. Now this seems confusing, and why are we going to need it? We might look at this a bit later. For now we're just going to try and figure out how we actually get these things. So it will take too much time in this video to explain everything. So that's limits done. Let's do another example with some limits. Let's look at this one here. So we'll go a little bit quicker this time. What is the limit as x goes towards 2? So here's our 2 point right here. It jumps obviously there, and what we're going to see is that from the left and from the right they are going towards different places. From the left of 2 it's heading towards 2. From the right of x equals 2, f of x is heading towards 4. So one's going to 4, one's going to 2, therefore there's no limit. We don't know where it's going. From the left and from the right it goes to different places as I'm going to x equals 2. So no limit. What is the limit of f of x as x goes to 1? So it doesn't have, you don't have to pick points where it jumps. There's actually, we can evaluate the limit ever on the graph. Usually it's just quite easy because it's just wherever it was going. But as x goes towards 1, from the right, if I put my finger on the graph to the right of 1 and to the left of 1, they both head towards the same point, which is 2. I'm looking in the y direction of where they are both heading, and they are both heading towards 2. So therefore the limit as x tends towards 1 is 2. Alright, so that is our limits, our continuity, and our differentiability. We're going to look at just a couple of other random questions that they can ask with these graphs. See if I can get everything in. We got 5 and 6. We don't quite have 7. Let's go up a tiny bit. Alright. 3 more questions. So, what is f of 2? So this is just basically asking what is the y value when x equals 2. Instead of using x's and y's, we use x's and f of x. But remember, f of x and y are basically interchangeable. So basically this just says find x equals 2 and what is f of x at that point. So that would also be 2. When x equals 2, f of x equals 2 also. So my answer to that one is 2. Again, a similar question. What is f of -4? So x -4. Now this is an interesting question because the limit said it was 1 because it was going towards 1, but the actual graph, the actual value at -4 is -1. It's down here. It jumps. There's a hole here, a solid hole here, so it is actually at -1 at that point. This does not care about what the limit is. It is actually asking where is the graph at that point. Lastly, what is the value of f dash? Notice there is a dash here, very important. So the derivative. What is the gradient is what this question is asking. What is the gradient when x equals 2? When x equals 2, we want to find the gradient here. Luckily, this is just a straight line. So it's not a curve, we don't need to use any crazy algebra. Straight lines, we're just looking for rise over run. So this one is going up one across one, up one across one, up one across one. Its gradient is 1. A straight line, gradient, rise over run, 1. 1 over 1, or 1. Quickly look at a couple of other questions they can ask. They're actually similar ones, just with a different graph. So 2 more questions. One's what we just did, another one's a little bit different. So what is f of 2? So again, we're looking for x equals 2, and we're trying to find actually where the graph is at that point. There's a hole here, so it's not there. Solid hole there, so it is there. It is at 4 at that point. And lastly, this is a good question for what we're talking about, or what you guys were looking at the other day for turning points. So for what values of x is the gradient 0? F dash of x is our gradient. What values of x is the gradient 0? So remember, turning points have a gradient of 0. Remember, if we're drawing the gradient line or sketching the gradient function, it's got a positive gradient, and then it has a horizontal gradient which has no rise, so it is 0. Then it goes down, 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 then it also has 0 there, curves up. It's not differentiable at that point, so definitely does not have a gradient there. But actually, this line going straight across here has a gradient of 0. This line going straight across here has a gradient of 0. And this point here will have a gradient of 0. So there's a few points. There's a few points and actually a few regions. This is a region where the gradient is 0. And this is also a region here where the gradient is 0. So we have to express that properly. So we're going to use mathematical terms to do it. Probably technically you could just write it using words, but we want to use some mathematical symbols. So the easy ones are just there, there, and there. So let's do them first. So it's going to be x equals -4, -2, and 4. So those are just the single points where the gradient is 0. But then we have 2 other regions. So then we also have and. So notice that at 1 and at 2, this graph is not differentiable because it has a corner and a jump. So it's inside that bit. So I'm going to write x is strictly smaller than 2, strictly bigger than 1. If I'd put an equal sign there, it would mean at that point as well, but actually it's not differentiable there. And then we also have the other region, which is from 2 to 3. Less than 3, bigger than 2. So at all of those points and those regions, the gradient of this graph is 0. Alright, I think that's all we have time for today. Hope it made sense. It is a little bit confusing. It's a little bit hard to kind of comprehend why on earth we would want to learn this. It's quite abstract, but it is useful. And we'll look at where the uses come in a bit later on. Alright.